So, welcome everyone, and welcome to the Programming on Accelerators workshop organized by Castile, the coordination action of EuroCC project. I'm Martina Di Renzo from Cineca, the leading partner of EuroCC Italy, and I'm going today to manage the event. I start by presenting you how the event is structured, and so I share the agenda. And today we'll start with a general overview by Mathi Krishnasamy from the NCC Luxembourg. He will go in depth with the JPU architecture and the CUDA programming model. And he will explain how to program the GPU with a particular focus on the memory management, which represents always a problematic issue for this type of device. And lastly, he will present some algorithms and a related final demo. And then second speech will be by Özkan Dulger by NCC Turkey. And we'll deal with performance optimization and efficiency. And we will see how to optimize the use of a GPU, both from the point of view of memory and computation. And then we will look at how to optimize the two main features of HPC. And the third and final speech will be by Luca Ferraro from the NCC Italy, and he will address the topics of parallelization and the use of multiple GPUs. And so we will touch the parallelization of intra-GPU execution, and then he will extend the discussion to the multi-node execution. And it will be presented how to use the entire cluster to perform computation and decrease the time to solution. And finally, he will conclude with a final demo. And given the size of the workshop, we will leave a 5 minutes break between one presentation and the next. And we will conclude with a Q&A session to give you more space to pose your question. And but before going to the first presentation, I will show you a brief video of a couple of minutes reporting a brief overview of EuroCC and Castile activities.
Ranging from the areas of health and food security to energy and the environment, we are facing more and more societal but also technological challenges. High-performance computing, or HPC, in combination with HPDA and AI, provides the means to tackle not only these large, complex problems, but also to widen further use and uptake of iterative modeling and simulation technologies in academia, public administration, and industry by processing massive data and performing complex calculations at high speed. But what is the value of such a toolset without the competence to utilize it best? Thus, the European High-Performance Computing Joint Undertaking addresses this field by implementing the EuroCC project as part of their funding activities. Within the EuroCC project, National Competence Centres, or NCCs, are created over a period of 2 years in 33 participating countries. These NCCs are intended to serve as a single point of contact in each European country, bringing together the national stakeholders and thus boosting the use of HPC and associated technologies. To maximally utilize synergies between all participating countries and national competence centers, the coordination and support action, Castile, is in place and active on a cross-national European level. By providing access to the excellent toolsets and enhancing European competitiveness as a whole, we can better face the challenges of our time. Visit us at www.eurocc-access.eu.
So thank you for your attention. I can stop to share my screen and we can start with the first talk. So Mathi, okay. So Mathi, if you're ready, I give you the floor.
Yeah, thank you, Martina. So I will start with my presentation.
Okay, great. Thank you.
Can you see my screen now?
Yes, very well.
Okay, thank you. Hello, good morning to everybody. So my name is Mathi Krishnasamy. I'm working as a postdoctoral researcher at the Luxembourg University. Today I'm going to talk about this very basic GPU programming using the CUDA programming language on NVIDIA GPUs. So we will cover these following topics today. Because when we talk about this CUDA programming, we also just want to know like the difference between this CPU architecture and GPU architecture. So we will discuss about that a little bit, and also we will also discuss like what is a streaming multiprocessor. Those are these CUDA cores on the NVIDIA GPUs, and then we will also talk about this memory hierarchy and then thread blocks, how the thread blocks are like organized within this NVIDIA GPUs and so on. And then the second topic would be how to do this programming on this NVIDIA GPUs using the CUDA programming model, programming structure, and then how to call the device, etc., etc. And then the third topic would be like this memory management, because when we write the program, CUDA program, we have to explicitly copy the data from this host. When we say host, that is like a CPU, host to device, GPU, and then you do the computation. And then once you've done the computation, you transfer back data to this host. That means like the CPU and so on. Yeah, so that is the most important thing as well. So we will discuss about that as well. And then to support all these arguments, we will show some examples with some numerical linear algebra routines, for example, like a vector addition and so on. Before we go into this CUDA programming and then using the GPUs and so on, we also want to know like a very fundamental idea why we need to use these GPUs and so on. Why we need because if you see like any supercomputers, almost all the supercomputers nowadays, they have like accelerators, either GPUs or some kind of like accelerators. Mostly it's like a NVIDIA or AMD, and then Intel is also coming and so on. So why we need these powerful computers? Because we need a powerful computers to run these large simulations where we can explore like science and engineering in depth with the help of these computers. Of course, the mathematics and science is very, very important, but along with that also we need like powerful computers to do this computation so that we can proceed further with understanding math and physics and so on in any science and engineering problems. So for example, like I just like listed out like 4 examples in astrophysics and CFD, turbulence, bioinformatics, and material science. Because in astrophysics we need to simulate like a lot of the galaxies and so on. They're like really vast in the universe. So with the normal computers, it might take like a lot of time, who knows. So with the powerful supercomputers, we can do like these kind of simulations very quickly. And then probably you might have seen like a nice videos from the documentary things and so on. All these things are possible. Imagination is possible only using these supercomputers and so on. And then the second topic is like a CFD turbulence also, because the turbulence problem is like nonlinear problems, and then with the just like using by pen and paper or normal computers, we cannot solve like these kind of turbulence problems to accurately predict this the turbulence in any scenario where the fluid is applicable. So in that case, also supercomputers are like very, very useful for this CFD turbulence problems. And then also similar to this bioinformatics and material science, because these are like a very complex physics phenomena. So of course we can define them mathematically, but solve them with just using normal computers, it won't be like very efficient. But using the supercomputers, we can able to solve these things very quickly, and then we can able to proceed further. Okay, what is lacking in this science and things? So this would make like a further advancement in this real-time applications and so on. Before I just said like some examples, now I'm gonna say like with numbers and so on. So in any like in science and engineering and artificial intelligence, we just need to do some arithmetic computations. For that, we need computers. And then in science and engineering, the problems are like defined by these partial differential equations. But we cannot solve these partial differential equations by hand or analytically because some problems doesn't even have a solution. For that, like we humans, we have invented like very long back ago, or still we are progressing on this direction, like numerical methods. Like this is the method kind of like approximate these differential equations. So when we use these numerical methods, we end up solving like matrices and vectors and so on. So to solve these things, we need like really powerful computers, because if it is like a 10x10 matrix, and then you can easily solve with a pen and paper or just like normal computer. Even if it's like even bigger, you can solve with normal computers, because the normal computers nowadays, you have like this multi-core architecture, like more than 5, 6, 8 cores and so on, you can solve. But if you have like really huge, large volume of matrix and vectors, you cannot solve with the normal computers. Then you need this super powerful supercomputers and so on. Even also the artificial intelligence, machine learning, we say like this very popular trending word nowadays, but these things also still need to do like a lot of arithmetic computations. For that, like we need like really powerful computers and so on. So, today the topic is about like GPUs, but also we want to know like what is the main difference between the CPU and GPUs? Why do we talk about the GPUs? What is this mysterious behind these GPUs and so on? The main differences between the CPU and GPUs, the GPUs has like many cores compared to CPUs, as you can see in the picture in the right-hand side from my screen, the green small boxes and so on. But even though the GPUs has like many cores, CPUs are like still faster compared to GPUs. That is like the frequency, how fast it can do the computation and so on. But since they cannot like handle many threads, since the GPU can do the many threads in parallel, so it kind of makes like more popular in the scientific community, so that we can do like a lot of computations on the GPUs and so on. You can also see like this Intel Core i7 processor as a base frequency, something like 3.8 gigahertz, whereas the NVIDIA Ampere has like 0.76, which is like a much less, but compared to cores, the Ampere cores are like more compared to this Intel Core and so on, i7, for example. So as I mentioned, like even though the CPUs is more powerful, GPUs has like many threads, so it can run like many problems in parallel compared to CPU. In general, in GPUs, the cores are GPU cores are grouped into a GPU processing cluster, and then each and every GPU processing cluster has its own streaming multiprocessor. It's called like ESMs, and then also texture process clusters and so on. This we will discuss in a coming slide. And also I have listed out like the latest GPU evaluation from the NVIDIA GPUs. So I think they have started something with the Tesla. This was like the GPU where people able to do some kind of like arithmetic operations using these NVIDIA GPUs and so on. So now we have like the latest GPUs are like a Pascal, Volta, Turing, and then Ampere, and then another one is also out in 2022. It's called like a Hopper. There is some nice video. I probably you would be able to see the slides after my presentation. Maybe you can click this link, and then you can see some nice video demo from the NVIDIA, so you can understand more like in a practical example of the parallel computing. So now we talked about this, like, okay, GPU has like many cores compared to CPU and so on. So what is the difference between the serial programming and parallel programming? Because we need to understand the difference between these things. Otherwise, if you don't see the difference, then we cannot use the GPUs effectively, because the fundamental idea of using the GPUs is the parallel programming. So in a serial programming, the entire problem can be divided into like discrete series of instructions, and then each and every instructions can be executed by one, and then this can be done by like just like a single processor. and then each and every instruction can be executed at the same time. Whereas on the parallel programming, entire problem can be divided into discrete part such way that it can be solved concurrently. That means like in a parallel, but in a pipeline manner and so on. So each path may have a set of instructions. Each part's instructions are executed different to thread and processor. So as we say here, like the parallel programming, so we have like a many parallel processor. Each and every parallel processor can execute different instructions or same instruction with a different data set and so on. So since it's like a parallel execution, we need to do some kind of like control things because we want to have like a control over the program. Because if you do like many things parallel, sometimes if you don't have a control over the program, then the results might be wrong at the end and so on. So nowadays, both the CPU and GPU and other processors can like embedded architecture can do this, can support this parallel programming and so on. So to support the theory which I explained just before now, so here is an example you can see. It's a nice illustration of the serial programming versus parallel programming. As you can see here, like on the left side from my screen, it's like a serial computing generic example, and then the bottom you can see like some kind of like a payroll example. So it's done like everything, just like a payroll, just like a one. It's done by like sequentially, and then all the instructions are like sequentially executed one by one, and then yes, it shows like this. And also another one is the parallel programming execution. As you can see here, the entire problem is discretized into like small problems. Or we can use like a many. For example, here the serial program, we have like only one payroll employee, but here we have like 2 employees and so on. And then we have like many instructions. They are like executed in a parallel with a parallel processor and so on. So now we will study more depth about this GPU architecture. Basically, the computers are categorized by 4 according to this Flynn's taxonomy. They are called like a single instruction stream, single data stream, and then single instruction stream, multiple data stream, multiple instruction stream, single data stream, and then finally multiple instruction streams, multiple data streams. This single instruction stream, single data stream is like a very serial case of example, as you can see here in the right side picture from my screen in the topmost left corner. And then also the single instruction stream, multiple data stream. It's kind of like a very useful for like science and engineering application, because when we do like a vector addition, we just need to like one instruction like addition, but we have like different data. So one instruction can be executed on the multiple data set and so on. So this is a very quite interesting. Mostly we do the computation based on these things. And then the third one is multiple instruction stream, single data stream. It's not like quite useful because it's not like we can achieve like a lot of parallel efficiency and so on. And then the final one is also it uses for like a very special cases, but not like mostly widely used for science and engineering application and so on. Finally, so why I talk about this thing is that because I just want to say what is a GPU architecture, because the GPU architecture is based on the single instruction multiple threads. That means so every thread can execute the same instruction but using the different data and so on. So that is a specialty, whereas on the CPU the one is one thread can process like many data with using the single instruction, whereas here on the GPUs we can do each and every data can be executed on the single thread and so on. So that is called like it's SIMT. So I have listed out, I just like put some points about these latest GPU architectures, and then their how the cores are like organized there and so on. For example, like Ampere as like GPU process cluster, 7 GPU process cluster, and then 42 tensor process texture process cluster, and then 84 SMS and so on. Similarly, the Volta is also very similar configuration and so on. The main interesting fact is that like each and every SM, like streaming multiprocessor, you can see here, in the right-hand side of the picture from the screen, in the bottom one, you can see like I just like enlarged one small block that is called like one streaming multiprocessor. And then you can have like a 7 GPU processing cluster. In the top you have 4, and the bottom you have 3, and so on. So each and every streaming multiprocessor, you have like a L1 cache up to 128 kilobytes, and also L2 cache is like a shared between these graphical GPU processing clusters. You can see like this blue bar between these four GPU processing cluster, and between the 4 GPU process cluster and then the 3 GPU process cluster, and so on. And then the latest one, probably you would have seen like some old GPUs and so on, like you would have seen like different picture, but this is like a very latest ones. So that's why you see like something like Arctic Core. This is for like a more advanced, for more like a rendering applications and so on, where we can use these Arctic Cores. And then also the latest GPUs are like tensor cores, where we can do like multi-precision computations. This is very quite useful to speed up the application in machine learning and artificial intelligence and so on. Finally, we have like this programmable shading cores, which is like a very typical CUDA cores, where we can do like normal computation using like a double precision or single precision and so on. So as I mentioned before, like the CUDA GPU architecture is based on this single instruction multiple thread, which enables programmers to do like thread level parallelization in the streaming multiprocessor, which gives like a data kind of parallelism on the GPUs. And also like the GPU's efficiency is measured by the occupancy. This is called like the maximum active warps can be supported by the multiprocessor, because each and every GPU, they have some limitations how many GPU warps they can support during the computation and so on. I will discuss about this, what is warps, in the final point. And then also in streaming multiprocessor, since it's like they are like based on this scalable multi-array thread, which allows us programmers to do like create like 2D, 3D, and 4D threads. This is not possible in a CPU as far as I see. So since these kind of things are possible, like you can create like a 2D thread block or 1D thread block or 3D thread block and so on. So this is typically called as a cooperative thread array. What we do it like a 1D thread, a 2D thread, and 3D thread, and so on. So typically on GPUs and the NVIDIA GPUs on CUDA programming, we say it's like a warp. Each and every warp has like a 32 threads. That means when we have the thread blocks, when we execute the application, each and every, let's say you have like a 64 thread you create, and then first to 32 will execute on the streaming multiprocessor once it is done, and the next 32 will execute after this first 32. So it will be like always like in a pipeline. So it's not like if you create like a 10,000 threads, all the 10,000 threads will execute on the same streaming multiprocessor. So it will execute by like 32 on different streaming multiprocessors and so on. So this is because, as I mentioned, like each and every GPUs, they have like very unique features and so on. That's why they release each and every 2 years or something like new architecture. To completely use this new architecture during the compilation, we have to use this compute capability flags. For example, like this Pascal and Volta, you have to use like SM-70 or SM-72 and so on. So this I will show during this example demo and so on. Okay, so far we have seen the basic GPU architecture, CPU, why we need a parallel programming, serial programming, and so on. So now we're going to see how the threads are like created in this CUDA programming language. So as I mentioned before, we can create like a 1D thread and 3D thread, 2D thread and 3D thread. So these are like declared in the CUDA programming as like a dim3, and then this is just name. You can have a different name and so on. But the dim should be like the class should define this variable and so on, grid variable. So the thread variable. So this is a grid and block. So you can have like different dimensions. There's a first example, the 2D grid and thread block. It has like you can see like 3 columns and 2 rows, and then each and every grid you have like 4 columns and then 3 rows of a thread block that you can see in the top picture from right hand side from my screen and so on. And then also another example like a 1D grid block and grid and thread block. This is also a similar thing that you can see in the picture in the bottom one on the right hand side from my screen. So to get this the index, you need to go like a block IDX and the multiply block dimx plus the thread IDX and so on, and then you can get like for example, if you want to get like a 515 thread, you have to use these calculations like 2 multiply with the 256 plus 3 and so on. Okay, so finally, so we know like these thread blocks are like existing CUDA programming. So how do we call them and so on? So for example, like I just want to give you some quick example here. So this is like a hello world example that we just like imagine that you have like main program and then you just call the hello world program that prints this hello world. But whereas if you want to call this function in the CUDA programming, we have to have like this bracket within this bracket. Between this bracket should be located between this function and then the function call arguments and so on. So you open a new bracket and then you include here like a grid and block. So this we will see more in detail during this demo session. So these are the main important the variables we need to remember when you do this CUDA programming. So grid dim specify the number of blocks in the grid, and then the block dim specify the number of threads in the blocks and so on. And then these are the index variables to get like the final index, because it's going to be like a 2D and 2D or 2D and 3D and so on. So we need to get like the final index because if you see here, everything is going to start from here. Like if you see the right hand side, the bottom picture, everything is going to start from like 0 to 255, and then another block it's going to start from 0 to 255. To get this final index, the global index things, we need to have like we need to specify these variable index variables. You have to use it like a block IDX or thread IDX and so on. So before we need to program, we need to understand. We need to know like a basic CUDA API. These are like very important. We need to know this CUDA malloc, because generally in CUDA programming, so we allocate the memory on the host that is like on the CPU, and then we need the computation on the GPU. To do that, we need to transfer the data which has been allocated on the CPU to the GPU. To be able to do that, we need to know this malloc. Usually you allocate the memory on the GPU, and then you transfer the allocated memory on the GPU to CPU to GPU memory. And then finally, we have to do this CUDA free to release this memory. And then the synchronize sync threads. And this is very important when we have like a block of threads, because when you do the parallel programming, the call can be like can be called quickly without finishing all the threads in the thread block and so on. So we have to make sure we synchronize all the threads. That means we finish all the computation using all the threads, then we can go to the next step and so on. And this is very important. If you don't use these things, sometimes we don't get the error, but if you don't use these things, mostly that you don't see the error during the computation, but if you don't use this one, you will get the wrong results in the final solution and so on. The same also CUDA device synchronize. This also is very, very important. When we do these unified memory computations, when we call the kernels, it will quickly quickly continue after the kernels before copying the data properly. So in that case, we need to have this CUDA device synchronized. I will talk about these things, what is unified memory in the upcoming, the final slides and so on. And this is also like the CUDA malloc managed for this allocating unified memory, because typically on CUDA programming, you can do two things. One is you can explicitly allocate the memory, and then you can transfer to the CUDA GPUs, and then you can do the computation, and then you can transfer back to the data to the CPU and so on. Or else you can just allocate the memory on the GPU, you can do the computations, and then you can do as a normal. You don't need to do any data transfer and so on. To be able to do that, we need to use this CUDA malloc managed CUDA API. So this is a quick comparison between like some latest GPUs, Turing and Ampere. So you can see like they have like almost like a very identical features, but the streaming multiprocessors like for Ampere is 68. And then also CUDA cores on each and every streaming multiprocessor. For Ampere is like 128 and so on. This is just to give you an idea. So what is happening? Because when we say like, because in the slide I mentioned that like we need to add like these things, compute capability flag during the compilation to be able to get the full support of the particular GPU use. So we need to know also like the GPU's features as well before we need to use them and so on. So this is just to give you an idea of this, some of the features of these latest GPUs and so on. This is also one more thing. So because this is just to give you like an overview, the global picture, but also we want to see like what is happening with the streaming multiprocessor and so on. So how many threads, warps it can support, like almost like a very identical 32 and 32. And then this is the compute capabilities, so we have to use them and, during the compilation flag. And then also you can see like maximum thread blocks, 32, and then maximum threads, each and every streaming multiprocessor they can support. Beyond that, they have to be in a queue. So and then maximum registers they can support and so on. So this information could be quite useful when we do like a really larger simulations on the GPUs and so on. Also, if something goes wrong, and then we can look back these things. Okay, this is what happening, and so maybe I should follow up with this. I should keep in mind these numbers and so on. And then the interesting thing is that like in these GPUs, you have like a freedom to configure, like reshape your memory, the shared memory size, because we talked about this cache, L1 cache, L2 cache, and then shared memory. And the memory that close to the chip, they're like very faster. So in case if you want to access the variable, or you have to keep the variable very close to memory quite often, then you can use this shared memory and so on. So you can also resize these things. And then you can do this like up to 228 kilobytes on the NVIDIA Hopper and so on. I think you can also do with the L1 cache also with the shared memory. So if you want the L1 cache more, you can reduce the shared memory. If you want to more shared memory, you can reduce also L1 cache and so on. So it's up to the programmer's problem approach. This is also very important before we start to do this CUDA programming, because we need to know, of course we want to run the code on the GPUs, but how do we tell the GPUs to execute this part on the code on the GPU and so on? To do that, we need to add this qualifier. It's called like a function qualifiers. The device means like this function only executable on the device, and then only callable from the device and so on. And then this is global. This is executable on the device, but it's callable from the host and also device only after the compute capability 3.2 and higher and so on. And then this is a host function qualifier. This is only executable on the host and then only callable from the host and so on. And then if you want to have like some inline function to be executed on the GPU, you can also do this function qualifier and so on. So this is just to run your functions on the different level on the CUDA programming. And then the bottom table shows us like how do we declare the memory on the GPU and so on. So when you say device, the memory stays like on the device, and then it stays like until the thread blocks or like doing the computation and so on. So that means like a application, entire application, the device can be visible to the threads. And then the constant is also like visible to the application until the threads are like doing the computation and so on. And then the final one is like a shared memory. So this shared memory is not like applicable for the entire grid and application. This is only visible within the thread block and so on. So you have to be very careful when you use this shared memory, how to use them and so on, because sometimes it's not like very straightforward. So you should know where to keep the variable within the thread block and so on to have like a very good computation solution. So now we have seen like so far many the CUDA API, GPU architecture, and then difference between a serial parallel programming, and then some motivation why we need to know these supercomputers and so on. So now we will see like simple hello world program from this CUDA example. So the main idea here is like we use the GPUs, either run this part of the computation on the GPU or entire computation on the GPU. For example, in this case, we're going to run this, how to print this all over the application on this GPUs. So to do that, as I mentioned, like we have to ask this function qualifier so that it can recognizable on the GPUs. You can see like the right-hand side of the picture from my screen. The top one is like an example of the C program, and then the bottom was like a CUDA program. The C program is just like runs like a normal one. You just call the function and so on. But whereas on the CUDA program, we just need to have like this global so that it can be executed. This can be executed on this GPU. And then also I have added this synchronized thread, and then also I have also added this CUDA reverse synchronize to make sure that like all the threads are like synchronized before it can continue to this after the CUDA function call. In this case, it's not like necessary because we have just like a one thread, but this is very, very advisable to avoid this any errors in the computation and so on. So you can see here we need to have like this, as I mentioned before, also like we need to have this the parenthesis brackets between this function name and then the function call brackets. So I also mentioned this synchronized thread you need to have to avoid this any errors and so on. Most of these the memcopy calls are like synchronized calls, but some of the calls are not like synchronized. So that's why we have to use this explicitly the synchronized threads or CUDA reverse synchronize to make sure our computation is correct and so on. And then another one is we're going to see this vector addition example. So here we know like there's a very standard application like standard numerical linear algebra routine. We have like two vectors and then we want to sum these two vectors and so on. So basically what we do here is that like first we need to initialize the memory on the host. So we need to initialize like A vector and B vector, and then I just call it as like CS like out. And also we also need to do the same thing also like on the GPU. We also need to initialize the memory on the GPU using this CUDA malloc. So I call it as like a device A vector, device B vector, and a device out. And then we also need to initialize these two vectors on the host. So as you can see here, like A vector and B vector and so on. I initialize some values, just 1 and 2. And then we have to do this transfer the initialized value from CPU to GPUs because we want to do the computation on the GPUs. For that, we need to have some initialized values on GPUs. So we need to do this CUDA memcopy, and then we copy from host to the device. Here the host is like A and B, and device is like D-A and D-B and so on. And then we are creating this here, the thread block here. This is just an example. I'm creating like 64 thread blocks. And then we're going to call this a function. I'm calling the kernel function. So you can call here like a grid and then the block and so on. And then once this computation is done, we have to we have to do this mem copy because, of course, in the GPU, we done the computation. At the end, we want to get the solution from the GPU back to the CPU and so on. So then we have to do this mem copy again, and then this time we have to do like device to host. So this is the function call and a vector addition function call. This is what happening in the when we call this function here. This is calling the kernel function. So we are like getting this global index from the 2D index. And then we want to make sure, because sometimes you can also create like more threads. It doesn't have to be like exactly the number of the vector size you want to add or multiply. It can be many threads. But if you want to make sure like only the needed threads to access this computation, you need to put this some kind of like condition here. So I put like only the threads are only allowable, size of n and so on. And then we do the finally synchronous threads. So it does this vector addition. And then finally, as you see, like here, we copy back this data to this D out. And then we do this CUDA free. We release this CUDA memory, and also we release this host memory and so on. So this is a very simple case. And then we will go next into this matrix multiplication. So here you can see matrix multiplication function in C and C++. We need to use like 3 for loops because it's like 2-dimensional and so on. So this is probably you might have known like most of you what is happening and so on. I will just talk about this the GPU function matrix multiplication one. So here we want to have like a threads, the global index in a row and column. And then we just want to specify the width, because we're going to do this matrix multiplication using this phenomena, like each and every the piece of row from one matrix and piece of column from another matrix. We're going to multiply them, and then we're going to sum up them in a one index in the product. To do that, so you can see like each thread compute one element of the blocks of matrix and so on. So then here it goes with this the size of this one column actually. So in this case, the width can be here just 2 in this example here. So all the example code is available also in the slide. You can also see, probably you will be able to get the slides. You can get it from the slides as well, but I will also show this example later. So the same example there, which I shown you before, also this vector multiplication, vector addition. And so here we also need to specify the same thing, allocate the memory and so on for the CPU, and then for the GPU also we need to allocate the memory. And then the initialized value should be copied back to this, copy to the GPUs. And then we create this here, the thread block. This is just for example for like a 2D thread block. Yeah, so then the rest is like we need to call the kernel, and then it will, we just need to call this kernel, and then we need to copy back and so on. So this is also, I will show you more example in the demo. So finally, yeah. Finally, I will talk about this unified memory because in the beginning I mentioned like you can do like two kinds of computation. One is like explicitly transfer the data from CPU to GPU, and another one is like you don't need to do this explicitly. The CUDA compiler will take care of this memory transfer automatically as long as you use this CUDA API and so on. So by doing that, you can see like that there is a comparison between here, like without unified memory and then with unified memory and so on. We almost like we eliminate like 4 steps compared to without unified memory, which is quite simple because as a programmer, we don't want to think about like so much complicated routines and so on. So you can eliminate almost like the 4 steps and so on. So we can eliminate this allocate the host memory, and then transfer the data from host to the device, and then device to host, and also free this host memory and so on. In the bottom, you can see some picture to visualize these things. So when you can see like the left-hand picture shows like without the unified memory, and the right-hand shows like with unified memory. You can see that the entire memory has become just one memory where both the CPU and GPU can be accessible and so on. So this makes like more simple for the programmers, but it doesn't mean that it's going to be like a faster compared to doing this explicit memory declaration. So at the end, in the back end, it's happening with explicitly, but the CUDA compilers, it gives us like more free accessible as a programmer, so you can simply use this unified memory programming concept. So finally here you can use this CUDA malloc managed. You can see like I already commented out all these host to memory routines. You can just directly do this instead of CUDA malloc. You can just do the CUDA malloc managed. You can just declare the memory size. This can be accessible both from the CPU and GPU and so on. And then when you use this in unified memory, we should use this always CUDA device synchronized. Otherwise, we might end up some kind of like error in the solution and so on. So I will jump into now quick demo session. So we also need to have like, if you're using like some kind of like cluster, we need to have like the module. Otherwise, we're not able to do these things. So now you can see like I have modeled this system CUDA compilers and so on. So you can also check like the GPU that you're using here. For example, I am having this Volta GPU here. You can see the CUDA version here and things, and some of the memory usage, what is happening here and so on. But also I have like a very simple example to show you. So this is where you need to use like this compute capabilities, because this is Volta. So for Volta, we have like a for Volta, we have like this, we have to use like this support, the streaming like a SM70 and so on. And then I'm gonna use this check. This is simple program to check your CUDA device, query your CUDA device. So this is just the one device I have, and then you can see like Tesla, and then this number, the Volta 100 and so on. A global memory, shared memory block, the warp size is like 32 and things. So you can see like some basic information about the GPU that you're about to use and so on. So we will see now a simple hello world example. So here you can see like this is like a printing from this CUDA function. So it runs, and then we get this hello from CUDA function and so on. So next I will show you this vector addition on the GPU. So you can see here, like I have just like used like only 256 the vector size here, and then you can see that the similar function that I showed in the slide, the vector addition function. Then here you do this, you allocate the host memory, and then you allocate the device memory, and then you initialize this arrays here so that we can have these values. And then we copy back the values, the initialized values from host to device. And then we create a thread here because our value is like 256. So we need to have like 256 threads. Of course, you can also have more threads. It's not a problem. And then, so once we do this computations, we copy back. And then we also want to make sure, like this simple case, we just want to make sure like we produce the correct solution and so on using this CUDA. And then finally, we have to deallocate the CUDA free and then also the device memory and also host memory and so on. So what happens if you use 32 here? Yeah, still it's working, you see, because if you see here, I put like this condition here, so it should, the threads can only accessible this the index variables within this the size of n and so on. So beyond that one, the threads cannot be using any of these values. So this is one example, and then we will see now this matrix multiplication example. So I will compile this one. 70. So I'll just specify a number. So what happens here is that, so as I mentioned, like so we multiply, we take this one column, one row, and one row from another matrix, another column from another matrix, and then we multiply them, and then we sum the value, and then we keep this value in one global index in the product index matrix and so on. So this is what is happening here in the function. So the same thing also with the same thing with what we done with this vector addition. So we have to initialize this host memory, and then we have to initialize the value for the computation. So here I just use like 2 in each and every index is like 2. And then we have to allocate the device memory, and also we need to create this thread block here. And then we call this kernel function from the host. And then we copy back this computed value, and then we just check the verification. And then finally, we do this CUDA free. That means release this host device memory, and also free means just a host memory and so on. So the final example would be, right now I want to show you this unified memory. So okay, so here I will open this application now. So in the function, nothing happens with the unified memory. It's very identical to this that we've seen before with the vector addition. But here you can see, like I have almost like a commented out. For example, here you can see in the slide here, in the final slide. Here, like just like a commented out. So I'm just using this only CUDA malloc managed, just like initializing just the one memory that is visible for both the CPU and GPU. And then I initialize these values, and then because since it's going to be like visible for the both and CPU and GPU, we don't need to do any transfer from host to device or device to host and so on. So I also just commented out this one. The same thread blocks should be very similar to the normal one, the previous example. And then we call this vector add a kernel function. And then also we eliminate this, again, the data transfer from the GPU to host. And then we do the final verification as usual for the previous example. And then we just do this CUDA free because we haven't done any allocation on this CPU, so we can just eliminate these things. We just need to free this the CUDA free memory because the memory has been allocated using this CUDA API, CUDA malloc managed and so on. So now I think we've shown some example. We run this example, but you can see here, like I have added this CUDA device synchronize, but in some cases I haven't added that because here we need to add, because we don't call this CUDA memcopy. This CUDA memcopy usually wait until this kernel call is completely executed on the GPU. Otherwise, it cannot proceed further. since we don't have this CUDA mem copy, what happens is that like if you don't use a CUDA device synchronize, it will quickly further go into down like the thread, and from the CPU side, it will touch the vector add and then quickly will go into this verification line, the for loop. Because we don't have any synchronized call in between these things. So that's why we need to add this explicitly, this CUDA device synchronize. Otherwise, we will produce some wrong results. So this can be seen here, for example. So now I just commented out this one. I will do the same one. You see, there is error now. So this is a problem, but if you do this, if you do CUDA device synchronize, that means all the computation is like completely done before the values comes back to the visible to the CPU side and so on. So here, so now it's working. So yeah. So yes, so this is all I wanted to discuss today. So thank you so much for listening. So if you have any questions, you can always contact me. And then also after this entire session, I will also be participating in the Q&A session. I will answer also your questions if there is any. Thank you so much.
Hi, Mathi. Thank you so much for your presentation. And there are some questions in the chat. Luca Ferraro, our third presenter, have already answered.
Okay.
Yeah, okay. If you want to give a look.
Okay. Thank you, Luca. Thank you so much.
We have 5 minutes break, so you have time to read the chat and then answer to.
Yes. Yeah, I will do that, of course.
Okay. Yeah. Thank you. So we will come back at 5:35. 10:35. Okay.